Hello, class. Week 7 guided notes. We will be discussing integers and integer operations. And we'll begin our discussion with this scenario where we have a 6-foot tall person who is standing on a bridge that is 15 feet above a river, which is 10 feet deep. And we have a little image here to help us make sense of this. So if I were to establish some lengths here, how tall is the man? Well, he is 6 feet tall. I'm going to use the single hash mark like that to represent feet. If you recall, a double hash mark means inches, or you can also put FT for feet, whichever. But I'll do a single hash mark for 6 feet. He's on a bridge that is 15 feet above the water. So we have 15 feet is this length, and the river, where we are told, is 10 feet deep. All right, so here are all the lengths relative to this scenario. Let's answer several questions. What is the man's height? Well, that was answered in the prompt. It's 6 feet. Let me ask you another question that might sound strange. What is the position of the top of the man's head relative to the bottom of his feet? Here we're asking about what is a position of a part of the man, the top of his head. And we talk about position, we have to always establish a frame of reference, like relative to what? Like how far is this position away from something else? And so when I say what is the position of the top of the man's head relative to the bottom of his feet, I'm essentially asking how far is the top of his head from the bottom of his feet, which is just a complicated way of saying what is the man's height. Of course, we're assuming this man is standing. If he was sitting, we would have a different answer here. We would be answering what is his sitting height, which is different than what is his standing height. Anyway, so we would say that the position of the top of the man's head, we would say it is 6 feet above. So we'll just put this in sentence. Top of head is 6 feet above bottom of feet. I'm not going to write a sentence for every single one of these, but this is how you would describe this. And this is essentially answering what is the man's height. Let's answer the next one. What is the position of the top of the man's head relative to the surface of the river? So here we're asking for, effectively, how many feet from the top of his head down to the river. So we'd want to combine the 6 feet and 15 feet, and we would say 21 feet. So I'm just going to abbreviate, but in your notes you should probably fill these out in complete sentences. Head is 21 feet above the river level, or the water level. We'll just say above the river. What is the position of the bottom of the man's feet relative to the river bottom? Okay, so now we're saying the river bottom is down here, and the bottom of the man's feet is there, and what's the position of the man's feet relative to the bottom of the river? And now we're answering, well, how long is this segment? We would add the 15 feet and the 10 feet and get 25 feet. So we'll say the man's feet, not to be confused with a foot of measurement, are 25 feet above the river bottom. All right, so far so good. What is the position of the river bottom relative to the bridge? Okay, well, the bridge is essentially at the same level as the man's feet, so the bridge and the bottom of the man's feet are the same height. And we are now asking what is the position down here relative to the bridge. So we just want to reverse our statement, essentially. You'll notice it's the same distance as the previous question. We're going to have 25 feet, but now we're going to be describing something being lower than something else. So we would say that the river bottom is 25 feet below. So notice we have a direction that we're implying here. We had aboves and all the others, but now we have a below situation. So below the bridge. what is the position of the river bottom relative to the top of the man's head? Okay, well, the river bottom to the man's head is this total distance. That's going to be 25 plus 631 feet total, but the river bottom is below the top of the man's head. So we will say, I'm just going to copy and paste this thing. At least I want most of it. Below we'll just say the head. And the answer is 31 feet. Okay, now what we're doing here is we're describing how far something is from something else, and we're also indicating a direction by using the words above or below. We have mathematical tools for doing this as well by using what are called integers, positive and negative numbers. Positive numbers will refer to being in one direction, and negative numbers will be referring to the other direction. But then we have to establish what is our frame of reference. What are we measuring distances from what? We have to answer that question. That is always revealed by this relative comment. Let's read this sentence down here together. The notion of position along a two-dimensional path is dependent on establishing a frame of reference, which means that position 0 has been identified and positive and negative directions have been indicated. All right, so in this case here, I'm going to show you a little visual of what's happening here when I establish a frame of reference. So we're talking about vertical positions, and so I'm going to draw a vertical arrow with, I'll make this an arrow, there we go, with an arrow pointing in the direction of increase and pointing in the direction of where the positives are. Then you establish on this some 0 position. And then we have a positive direction and then a negative direction. Now usually when you're talking about height, we will establish that the positive direction is going up and the negative direction is going down, although you're welcome to change that up. All right, so when I say establish a frame of reference, let's focus on this first question that was asked here, relative to the surface of the river. What that means is that we want to position our 0, our number line here, at the surface of the river, which is right in this position. And then we can answer this second question right here. This is what I'm focused on right now. What is the position of the top of the man's head relative to the surface of the river? Well, the top of the head is 21 feet away from position 0. And so we could say, using an integer, a positive or negative number, that the answer to this simply is positive 21 feet. Positive 21 feet. Or we could just leave the units off and just assume that feet is implied and say positive 21 is the position of the man's head. But you really want units of measure, at least in your thinking. Might as well put it in our writing. And then if I don't change the frame of reference, and I say, hey, relative to the top of the water, so keep the same frame of reference that we see right here, what is the position of the river bottom? Right, so the river bottom would be at a position that's 10 feet below what we're saying position 0 is, so we would say negative 10 feet would be the river bottom relative to the top of the river, the surface of the river. But each of these, most of these questions do switch the frame of reference. Let's go back to the first question, not the man's height, but technically the second question. Right, what is the position of the top of the man's head relative to the bottom of his feet? Well, for that, we would want to shift our frame of reference so that we get the bottom of his feet is position 0. And then we say, okay, well, now where is the top of his head? Right, we would say it's at positive 6. So an answer here would be positive 6 feet. The next frame of reference is relative to the river bottom. Right, so I'm going to move my frame of reference so that it's now position 0 is at the river bottom, and then say, okay, what is the position of the bottom of the man's feet relative to the river bottom? And that would require us to extend my line a little bit, but we would say that's at position 25. It's 25 feet above position 0. And so we get to say positive 25 feet. What is the position of the river bottom relative to the bridge? Okay, so once again, I'll move my frame of reference, go relative to the bridge right there, and say, what is the position of the river bottom relative to the bridge? Well, it is at a position that is 25 feet below, so it's at this height. So that's at a negative 25 position. The negative indicates the direction, 25 feet away from 0, but below. So using an integer, I would do negative 25 feet. I'll define the word integer more formally in a moment, but an integer is really just any counting number, 0 or negative counting number. We'll define that on the next page officially. What is the position of the river bottom relative to the top of the man's head? And so then once again we have to shift our frame of reference, put position 0, relative to the top of the man's head, and then say where's the river bottom? It's way down here at negative 31. It's 31 feet below the top of the man's head. Okay, so we adopted the convention that if we're doing a vertical position, then being up is the positive direction, going down is the negative direction. So in our case, every time we were saying that we were 6 feet above something, right, we wanted a positive integer, a positive number as our position. And every time we were below, we had a negative. Now, of course, that's arbitrarily decided. I mean, it's possible that you want to do your frame of reference and rotate it, right, so that going down is now the positive direction, and that would be totally fine. It just depends on how you choose to say where's position 0 and which way is the positive direction. That's really up to the thinker. So this is what is meant when they say that to establish a frame of reference for a position of an object along a two-dimensional path, we need to position, or we need to do a couple things here. We need to identify position 0, say where that is, and then also identify which way we want to be positive, which way we want to be negative. If I had flipped my frame of reference so that going down was positive direction, then all my answers, their signs, would be flip-flopped. Right? These three would all be negative because above would be the negative direction, and these two would be positive because going down would be the positive direction. But again, that's up to the thinker. So let's say just formally here that we'll say up is positive. Put that formally in our notes so that all of our above answers are all positive answers. Okay, let's go to the next slide, number 2. Frames of reference are important in other contexts, not only position along a path, but other contexts here as we're going to see. For example, at a certain temperature, water will freeze. Now in the Celsius system, this temperature is called 0. Reading this here. In this system, temperatures that are above freezing are positive, and temperatures that are below freezing are negative. Note that in the Fahrenheit system, the freezing temperature of water is position 32. It should also be noted that a 1 degree change in Celsius does not equal a 1 degree change in Fahrenheit. I just say that for your information, but let's do a sideways frame of reference. So we have, we'll say this, we're doing degrees Celsius. And we have this notion that water will start to freeze at a certain temperature. So I'm going to put a little hash mark right through there. That's the temperature at which water freezes. And in the Celsius system, that temperature is 0. Let me move this down a little bit. 0 degrees Celsius is where water freezes. And then if it's warmer, then we go into the positive direction. And if it's cooler, we go into the negative direction. Now, notice that when I draw my frame of reference arrow, I only put an arrow pointing in one direction. Now, sometimes people like to put an arrow on both sides to show that it goes forever both directions. But what's confusing about that is it doesn't, if you only do an arrow in one direction, that indicates the positive direction. So that's our convention. Because it's possible, if I want, I could say the positive direction is that way and the negative direction is that way. Because it's up to me to choose which way the positive and negative directions face. But if you do a single arrow, then it communicates to the viewer that which direction is positive. Now, of course, if we're in the Fahrenheit system, the temperature at which water freezes in Fahrenheit is a different number. It's 32 degrees Fahrenheit. And just curious, do we know the temperatures at which water boils given these two systems? Let's move all that over here a little bit. We'll say H2O boils. It occurs at a temperature that is 100 degrees in the Celsius system. This is one reason why Celsius system is a nice one. It goes from 0 to 100, from freezing to boiling. In the Fahrenheit, I don't know if you knew this, but it's 212 degrees Fahrenheit. And as you can see, here we have a change of 100 degrees. Here we have a change of 180 degrees. That indicates that a 1 degree change in Celsius is not equivalent to 1 degree change in Fahrenheit. But here we obviously have some frames of reference going on here. So when I say, hey, it's 72 degrees Fahrenheit outside, what I'm saying is that we are 40 degrees above freezing. Or if I say that in Celsius, it's 26 degrees Celsius outside, I'm saying, well, it's 26 degrees warmer in Celsius than 0, which is the freezing temperature of water. So when you give a temperature, it's all relative to some position we call 0. Here's a financial context. Suppose you have $4,000 in your bank account. I'm reading this now. As an emergency fund, which you establish as position 0. Negative values indicate balances below your emergency fund level, and positive values indicate balances above your emergency fund level. Fill in the table below. All right, so if we're saying $4,000 is your position 0. So if you're at $4,500, then we're at position positive 500. So the relative value, when I say I'm at a position of positive 500, I'm saying that's relative to my emergency fund level of $4,000. So I'm $500 above that. If my balance drops to 1,000, then I've gone below my emergency fund level by $3,000. And so I would say I am negative. So we'd say we have a negative $3,000 is my balance. That's relative to my $4,000 that I want to be position 0. So this tells me that I'm not necessarily in debt, right? Because I have money in my bank account, but I want to get back up to my 4,000 emergency fund level. And I'm $3,000 below that right now. Here, if you know the relative value, let's say that we're at a relative value of positive 1,200. Now, if there's no sign in front of it, always assume that we are talking about it's a positive number. So if we're at $1,200 positive, and that's our relative value, that means we are $1,200 above my emergency fund level. So my actual bank account would say that I had $5,200 in it. If I'm at a negative $500, that means I'm $500 below my emergency fund level. So that means my bank account, I actually only have $3,500. So I'm $500 below the 4,000 figure. And if my balance ever hits 0, then that tells me I'm $4,000 below what I want it to be. I could put another entry in here. What if your relative value is 0? Then that would tell you that you're at your current emergency fund level, because you're at position 0, which we have defined to be that $4,000 balance. Time is also dependent on establishing some frame of reference. For example, what do you mean when you say it is the year 2020? Well, we've all agreed, this whole planet essentially has agreed that time 0, year 0, will be the birth of Christ. And so when we say that it's 2020, positive 2020, we're really saying that we are 2,020 years after or above the position 0, which we're saying is when Christ was born. And if you were to give a BC date, that would be like a negative year. So like 300 years before Christ would be a position of negative 300 years. You know, if we had decided that when the country was born in 1776 that was year 0, then our year system would be totally different. We wouldn't be saying 2020. Also, what does it mean when I say my age is 21 years? Well, that's always, there's an implied starting position 0, like when you were born. You were born at time 0, and currently you're at 21 years past that. So we say we're 21. That's why everyone, like you get a room of 10 people who are all different aged, and you say, hey, at the same time, everyone say your age. Everyone's going to say a different number because they all are working on a different frame of reference. They're all measuring today's date by, in reference to the year that they were born. So let's draw up maybe one thing here. So we have a timeline, and we would say year 0 is when Christ was born. So we'll just say birth of Christ. Whether or not you're a believer, we just say that 0 is the year of birth of Christ. And so when we say it's the year 2020, we're at a positive position, meaning that we're after. So 2020 years have elapsed since the birth of Christ. So we do have definitely a frame of reference. And of course, before Christ years would be like negative 1,000 years BC would be 1,000 years before Christ. Okay, now let's formally define what these integers are. The set of integers represented by the symbol z. Now you're going to see a bold capital Z that stands for the integers. Sometimes you'll see a Z with a double bar in the middle like this, because when you're writing, it's a pain to do bold when you're writing. And so instead of doing that, often you will see people do something like this to stand for a bold Z. Anyway, it's a bold capital Z, and it stands for the set of numbers that include the whole numbers and the negatives of the whole numbers. The integers negative a and a are called opposites of each other, and each integer can be thought of as a number that has both magnitude and direction. All right, so I don't want to say too much here. Let's go back to what a whole number is. If you recall that the whole numbers, let me write that over here, was a bold W, or you can do a W with a bar, double bar like that. The whole numbers were 0, 1, 2, 3, etc. Remember the natural numbers? The natural numbers were called the counting numbers. It's the same set, but no 0. If you throw all the opposites of the natural numbers, so negative 1, negative 2, negative 3, etc., then combine that with the natural numbers and put 0 in the list, right? And then we have the integers. And so the integers, here's several of them. Those are natural numbers. 0 and on is the whole numbers. And then if we tack on all the opposites of the natural numbers, all the negatives of these natural numbers or whole numbers, the negative of 0, by the way, the opposite of 0 is still 0. So 0 is the only number that when you do the opposite of it, you don't change it. And when I say opposite, I say, hey, what's the opposite of 2? You would say negative 2. And vice versa. If I say, hey, what's the opposite of negative 4? You would say positive 4 is the opposite of positive 4. If you were to use Venn diagrams to represent these things, then the smallest set here is the natural numbers. So you would have the natural numbers as one circle, and then the whole numbers is a bigger inclusive set. So the whole numbers is a superset of the natural numbers. The natural numbers is a proper subset of the whole numbers. So you should draw the circles inside each other like this. And then even more inclusive, a bigger superset of all of it is the integers. So this is the relationship between these categories of numbers using a Venn diagram. And then we have, when I say that each integer, I'm reading this now, can be thought of as a number that has both magnitude and direction. So when I say, hey, think of negative 5, what does that mean? You would say, okay, well, it's 5 units away from 0. So that's what I mean by it has magnitude. It tells you how far from 0 it is. And the negative implies that we're in a certain direction, whereas a positive would imply the opposite direction. So every positive and negative number can be thought of as having both magnitude and direction relative to position 0. And the last set of instructions here are to place the integers seen below on a number line. So we'll do a number line with a single direction for the arrow and indicate a positive. Put 0 somewhere on this number line, and then you do little hash marks for each integer and make them equally spaced, ideally, right, etc. And then the other direction, negative 1, 1 away, 1 left of 0. Negative 2 means 2 left of 0. Negative 3 means 3 units left of 0. 4 units left of 0, etc., right? Going that direction. And of course, now that you have a frame of reference, you could use this to, you can go up here to the birth of Christ and position 0 at 0 and then measure things from there. You could, if you need to, you could rotate it and do it like heights, right? Or if you want to make it increase the other direction, right? You can make it increase that way or increase down, or you can even do it along a diagonal. But you just need to have some sort of two-dimensional path, like a line, essentially, that you say, okay, somewhere on this line is position 0, and positives are one direction and negatives are the other direction. Now, convention, when you draw it horizontally, we tend to make it positive direction, be off to the right. But that's just a convention. You might need to do it the other way around sometimes. Number 3, integer addition is the act of combining two integer values to form a new integer. Now, a common manipulative for modeling integer addition is the use of integer chips, which are small disks with a different color on each side. One chip is either plus or minus 1, depending on which color is face up. We're going to use integer chips to model the following operations. All right, so addition is combining. And one good way to think of integers is to place it in a context such as the money context. Let's say a plus 1 means like you have a credit for $1, and a minus 1 means you have a debt for $1. So if you combine a plus 1 and a minus 1, you expect those financial values to cancel each other. If you get a credit for $1 and then you incur a debt for $1, then your net value is 0. Okay, what that looks like with integer chips. Let me show you a virtual manipulative that uses integer chips as these little circles. The yellow ones stand for the plus 1, and then the red ones stand for the minus 1. And in reality, students who are working with these integer chips maybe have actual physical chips like poker chips, right, where you flip the piece over and one side it's red, the other side it's yellow. But for this digital thing, we just have a plus sign on the yellow and a minus sign on the red. And so if I'm going to use the combining idea, so if I say, here's my positive 1, here's my negative 1, and I want to combine them together, and they form a pairing that's called a zero pair because they offset each other. And in fact, in this manipulative, if I take the red and try to put it on top of the yellow, they cancel each other and go away. And if I want to bring them back, I just tap these symbols and it brings back. Oh, they canceled. I think you can also just drag it into your table. This grid here is called the table. In fact, while I'm here, let me just show you what happens. If you want to clear everything at once, just say start over. If you click on positives a bunch of times, it'll just throw a whole bunch of them down at a time. If you want to flip them all to negatives, you can do this thing here that changes the signs, which is, I'm just clicking the opposite tab on the top left. Start over again cancels everything. You can add pairings. That's like adding a 0, because a plus and a minus together is like a 0. And so what we have on the board right now, on the grid, is the value 0. Because when these are combined, right, they have no value. They cancel each other. You can also put a bunch of these on the board and then a bunch of negatives on the board. Oops, they canceled. Sorry, didn't mean to do that. Let's put a bunch of positives. And then I'll put a bunch of negatives over here. And now if I tap this, I think the negatives will just show up. Okay, yeah. So there's some playing around you could do here. But let's say I want to clear just some of these. Just tap some of them that you want to clear and then hit this clear mark chips the bomb. And I'll just clear out the ones maybe you didn't mean to put there. And then you can say start over, clear everything. Okay, so I'm going to be using this tool a little bit, but mostly I'll be representing the chips here by putting drawings, which is what you're going to be expected to do to fill in your guided notes and to do your homework, is just to draw a representation of these chips. So you've got this positive chip and a negative chip, and the act of addition is to combine them, just like it means with adding whole numbers. So, and then when you combine them, they cancel each other, and they take on a value of 0. So it suggests that 1 plus negative 1 will be 0. Now notice I put both numbers in parentheses. That's simply because when we start getting negative numbers involved and there's an operation that sometimes having these signs right by each other without parentheses starts to look confusing. For example, if I were to write this as, 1 plus minus 1, this can sometimes be a confusing looking expression to students. And I prefer, when I'm working with integers, is to put the numbers after the operation. So the operation is here. So the numbers after the operation, I like to put them in parentheses. You're going to see me do that consistently through the notes and homework, although I'm not going to insist that you necessarily do it in your own writing, although it's a good habit. And sometimes I also put the first number before the operation in parentheses too, but that one is debatable. Most people don't bother putting the first number in parentheses. They'll write the operation, but then the second number, they like to put in parentheses, just to avoid this confusion of having an operator followed by a sign of a number right away can be a confusing notation. All right, so this is one way you might see it written, or you might see, I don't have to put either one in parentheses, and this means the same thing, combining a 1 with a negative 1. All right, so when you're doing this in your homework, here's a good way to write this. You could do, put the positive 1, and then say plus, and then put the negative 1 chip, and then you can write equals, and then you can put them together, right? You just combine them, but those zero out, and so you could just say that that just is a representation of 0, and so we have our answer of 0. So we supported the claim that 1 plus negative 1 is 0 using integer chips. Okay, let's do something negative 8 plus 3. Let's go back to the manipulative, the virtual manipulative, negative 8 plus 3. So I'm going to do a representation of negative 8. So I need to have 8 debts, essentially. It's like I owe someone $8. There it is. I think I have negative 8. Then I'm going to do a second number that's going to be positive 3. There we go. So I have positive 3 on the board. Let's make sure those are the numbers. Yeah, negative 8 and positive 3. So when you combine these, right, when these get combined, I'll just put them side by side, you can see that some of the positives will offset some of the negatives. Right, this positive will cancel that negative, cancel, and cancel. And then what are you left with? Well, I have negative 5 remaining on the table. So it's like saying you have a debt of $8, but then someone gives you a credit of $3, and when they combine, you now still have a debt of $5. It's nice to think of this as having a financial context. Okay, so when you're trying to show this on paper, let's do the negative 8 by just putting 8 circles. And if you want to be even lazier, you could just do 8 negative signs. And those are the 8 negative chips. And we're going to combine that. We're going to add that to 3 positive chips. And then you get your pairings that cancel each other. Right? Visually, you would put those 3 pluses there, would cancel those negatives, and those would all go away. Right? These 3 would all cancel each other. And so you'd be left with, oh, I'm now seeing that I didn't do 8, I did 7. Notice I don't have enough negative signs. There we go. And so when the 3 negatives cancel with the 3 positives, and we're left with 5 negatives still. So the result of this combination is a negative 5. And maybe you could do 0, 0, 0, but then there's still 5 negatives. Something like this could be your tool for using integer chips to show it on paper what it would look like. And if it's helpful, you can maybe put these in little blobs. So there's negative 8. We're adding it to positive 3, and we're getting a result that is 0, 0, 0, but then 3 negatives. So we get a result of negative 5. In fact, let me put my answers just above next to the operation, not down here. Okay, let's keep this work separate. I'll maybe write a little bit smaller for these other ones. Now we're doing 3 plus negative 8. So let's go back up to here. Let's clear everything. Now we have 3, 1, 2, 3, and then let's make a negative row, and then put the negative 8. Wait, am I doing that right? 3 plus negative 8, yeah, okay. One more, there we go. Okay, so there's 3 plus negative 8 combined, And then, of course, we have these 0 pairs that can be ignored, and we're left with -5 still. Okay, notice what this is showing us is that if you start with 3 positives, so let's say we have plus, 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 there's the 3 positives. We're going to add that to the 8 negatives, 1, 2, 3, 4, 5, 6, 7, 8. We're going to wind up with getting 5 negatives still. Don't worry about putting the zeros in there if you don't want. Notice I put the zeros here, but feel free not to put them if you don't want to. What this is essentially showing us is that addition is still commutative with the integers, right? It doesn't matter how you combine these chips together, which one's on which side. Addition is still numerically commutative when you have integers. So it's commutative with whole numbers, also commutative with integers. And when we add 2 negatives together, add a -2 plus a -4. Okay, so let's delete one of these. Delete that. So there's my -4. We're going to combine that with now a -2. And when you just put negatives with more negatives, you get more negatives, right? It's saying you have a debt of $4 and someone gives you another, now you owe someone else $2, and so now your total debt is $6 you owe. So it's like combining 2 debts, and you have a larger debt. So you're further away from 0, but in the negative direction. So a representation of this would be we have a -2. We're combining that with a -4. Oops, I don't know why I put it. There we go. And when we combine those together, we just have 6 negatives now. 1, 2, 3, 4, 5, 6. So this supports that we have -6 as a result. And I forgot to put the -5 there. All right, so that's integer addition using chips as a model, and thinking of the pluses as maybe credits and the minuses as debts, and seeing when you combine debts and credits what happens. When you combine debts with debts, what happens? Another approach to integer addition is to use a number line. So we're going to begin at the position indicated by the first addend. So if I'm doing -8 plus 3, then I'm going to make a number line. Let's do only one arrow. Let me get rid of that one. And put a position 0 on here, and then go start at position -8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here's position -8. We start at the first addend. Then if the second addend is positive, move to the right. So when I add 3 to -8, we go to the right 3 units. This is when we add 3, and that takes us to a position of -5. All right, so now let's do the commutative property here and see if I do the process but backwards if we get the same result. We saw that we did with the integer chips, so let's see what happens if I do this number line approach. So put 0 on here, and then start at the first addend, which is position 3. So we're starting here. And then the next line here says if the second addend is positive, move to the right the indicated amount. And if the second addend is negative, move to the left the indicated amount. And so since we're adding a -8, we want to go left 8 units. All right, so we can count them out like 1, 2, 3, 4, 5, 6, 7, 8 is where we're going to wind up. And total, we added a -8, so we went left 8. And that takes us to position, and this again is -5 position because it's 5 hash marks to the left of 0. So you can see the number line approach supports the idea that integer addition is still commutative. And let's do this last one here, -2 plus -4, using a number line. Let's say 0 is here. We're going to start at -2 position. And if I add -4 to -2, then that's going to take me left 4 units. So 1, 2, 3, 4. And this is the jump we make when I add a -4. And that takes me to the -6 position. Right, so that's just confirming what we did with integer chips up here to get that -6. So you'll notice that the 3 that we just did right here were the same as these 3. Now, which model should you teach children? I personally like the integer chips because it allows us to talk about combining debts and credits, and so it gives them a financial context, and it just helps them understand how math is useful to modeling things. Like down here, it just feels like it's a set of rules, and I'm doing stuff that doesn't seem relevant. But when you do integer chips and you talk about how the chips are positive, positive is a credit and the negative is a debt, all of a sudden it has a meaning to a child. And children who are learning this are old enough to understand financial matters, at least the very basics of it. And also the integer chips give them something physical to handle and manipulate, which is engaging for the child. So I prefer the integer chips as over doing a number line approach, but they both are different models for doing integer addition. Okay, the next segment here is on integer subtraction. Integer subtraction can be imagined using the takeaway or the comparison conceptualization for subtraction. Use integer chips to calculate the following operations using both conceptualizations. Okay, so let's start with something that's familiar. And notice my convention here. I'm putting both numbers in parentheses still. It's very common that you will not see either number in parentheses. So this one will look like 6 minus 2. Down here, you'll see 2 minus 5. And down here, you'll see -7 minus -2. You can see why it starts to become cumbersome when it looks weird when you see -7 minus -2. When you say it like that, it sounds like you said the word minus too many times on accident or something. I prefer to always putting both integers in parentheses is nice, so it's clear that this is a negative number and we're subtracting, and this is a negative number. But at least you should put the subtrahend, which is the second number in the subtraction, in parentheses. It's debatable whether you should put the minuend or the first one in parentheses, but you'll see in this whole table I put both of them in parentheses. Anyway, 6 minus 2. Okay, so we're going to do the takeaway model. Let's clear everything and start with 6. Start with the minuend. So there's 6. Now I want to remove 2. So I'm going to take 2 credits and then bomb them. And what's left? 4. Right, so this is an obvious, this is just a reminder of what we did with subtraction of whole numbers. This time I want to do let's do a representation for 6. I'll put a 6 and a colon and then just do a representation. I'm going to go ahead and put the 6 pluses. I'll put them side by side like this. So there's my 6. And now we're going to take away, because subtraction, when you see subtraction, it means take away. We're going to take away a positive 2. So we're going to remove, oops, there we go, 2 plus signs. And so the result is that we have 4 plus signs. So we have an answer here. So I'll put maybe my answer, I'll put it just right here. The answer is 4. And maybe I'll highlight the ones that got removed. We started with 6, we removed 2, and we're left with 4. Okay, I think let's go ahead and do the first column of this. Let's do nothing but takeaway models to finish out all these problems, and then we'll go over here and do the second column, the comparison models. All right, so let's do 2 minus 5 next. This is where a child might start to feel confused, because how can you remove 5 things from 2? Like someone said, you have 2 candy bars and I'll take away 5 of them. A student will be perplexed by that. Because what does it mean to have less than 0 candy bars? Maybe it means it's a debt of a candy bar. So maybe doing this in a context where debts feel more sensible, like you have 2 credits and now you incur a debt of 5. So what's your net value? Well, to model this, let me clear everything out. We have, we're doing 2 minus 5. So let's start with a representation of 2. And I want to take away 5 yellows, but there aren't 5 yellows. So what we do is we add 0 pairs. And we add enough of these 0 pairs so that to the point where I can then see 5 yellows that I can take away. Now, I'm going to pause right here. The value on the table is 2, because I see 2 positives, and then I see a plus minus 0 pair. Right? The value on the table is 2 still. And I can add as many 0 pairs as I want, and the value on the table stays 2. Right? You can keep going. Add as many as you want. You just want to get to the point where you can see that you obviously have 5 pluses you can take away. Remember, we're trying to remove 5 credits from 2 credits. And so let me delete some of these pairings. I want to just keep as many pairings on the table as I need in order to see, there we go, in order to see 5 plus signs. Okay, so I'm going to stop right there. Here's my representation of 2. And now I want to take away 5 positives. So now we're going to take away those 5 positives. And what's left? A dead of 3. 3 negatives. Okay, so in my work here, I would say, okay, let's do a representation of 2. Go back to black. A representation of 2 is plus, plus. And I want to remove 5. So we're trying to remove plus, 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 plus. Well, I only have 2 pluses, and I'm trying to remove 5. Well, so insert 0 pairings into the representation of 2 until you have plus 5s that you can remove. So there's a 0 pairing. Oops. There's a 0 pairing, and there's a 0 pairing. And now we want to remove 5, and we can remove those 5 away. And then the results is that we have 3 negatives left. And that is a representation of negative 3. Okay, so we can still take away a certain amount of yellows, even if I feel like I didn't start with enough yellows to remove. Like, I want to remove more yellows than I started with. Well, you can add more yellows by adding those 0 pairs. Let's do the next one, negative 7 minus negative 2. And I want you to sort of forget, all the rules you learned about this. You might have learned that, I can go make that plus, and negative 7 plus 2 means it's going to be negative 5, right? We know how to do this pretty quickly in our heads at this point, but we're teaching you models that you're going to be sharing with children who are trying to build these meanings. So let's try negative 7 minus negative 2. Let's go back to our virtual board here and start over. And negative 7. Okay, so I'm going to start with the dead of 7. 5, 6, 7. There's negative 7. And I want to remove a dead of negative 2. I want to remove negatives from negatives. I'm trying to take 2 reds away from 7 reds. Well, that's easy. Just take 2 of those reds and remove them. And what's left? 5 reds. Right? So when you're taking a smaller amount of reds from a larger amount of reds, it's easy. Same thing as when you're taking a smaller amount of yellows from a larger amount of yellows. It was easy. And so we started with a negative 7, which was just 7 negatives. 5, 6, 7. We wanted to remove, right? That's subtraction there means remove, but we're going to remove more negatives. We wanted to remove 2 negatives, right? So those correspond to, these last 2 there maybe are the 2 that we're removing. And then the results of this operation is that we have 5 negatives left, which represents negative 5. Removing negatives is like removing debts. When you remove debts, it's the same thing as giving yourself credits. Something to think about. Removing a negative is like adding a positive. Let's do negative 1 minus negative 4. Start over. There's negative 1. And I want to remove a negative 4. All right, so this is another situation where I'm starting with not enough reds to remove. So we can start, let me put that there, we can be adding our 0 pairs. because I have to drag those always. And you put that negative right there. And I want to get to the point, I want to do enough of these so that I can now see, okay, now I have 4 reds I can take away. So I've clearly done too many. I can delete a bunch of this. That's all I really needed to insert. So the value that's on the table currently is still -1, because it's a -1 with 3 0 pairs added to it. So it's -1 on the table. And now I want to remove 4 negatives. And what's left? 3 positives. All right, so our work here would be, okay, a representation for -1 is just a negative sign, but I want to remove from that 4 negative signs. Well, I only have 1 to start, so put the 0 pairings on there. Okay, so this is still a -1, and now I'm in a position where I can remove 4 negative signs. So I'm going to remove those 4, which corresponds to those 4. And then the result is we have 3 plus signs, which corresponds to an answer of 3. Okay, a couple more. Let's do -3 and then -6 from that. Now you probably already know the answer is going to be -9, but this is about modeling this. So let's start with -3. Okay, maybe we'll do this without the virtual manipulative. I'll do it up here, just representation of it. -3, so 3 minus signs. I want to remove +6. Oops. Remove +6 is what we're trying to take away from -3. Okay, well currently my representation for -3 has 0 positive signs involved, right? There's just 3 minus signs. And I'm trying to remove positives from negatives. Well, we're going to have to add 6 0 pairs then to do this, right? So here's 1 0 pair, 2 0 pairs, 3 0 pairs, 4, 5, 6. Now I have a representation of -3 that does have 6 pluses that I can remove. So we're going to remove those 6 pluses, which correspond to those 6 pluses, and then what's going to be left over? A total of 9 negatives. Right, so the result is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So -9. Same thing, we have 8 minus -4. So 8 is represented by 8 pluses. There we go. There's 8 pluses. And we want to remove, we're doing the takeaway model here for subtraction, remove a -4. So we're trying to remove 4 negatives, but there are no negatives to remove. So then put 4 0 pairs on here so that we can remove, right, these 4 negatives right there can go away. And then what's going to be left over? The result of this will be that we have a whole bunch, we have more pluses now. So we have the 8 pluses we had originally. There's the 8 pluses, and then now we have another 4 more. I think that's a total of positive 12. All right, so this is using the takeaway model. And when you're trying to take away something that you currently don't see, then just throw enough 0 pairs on there so that you can then take away what you need to take away from what you can see. Now let's talk about what the comparison model. Remember comparison model, when we said, hey, 6 minus 2, don't actually take 2 away from 6, but let's pretend someone had $6 and someone had $2, and we said, hey, how much more does that person have? Right? We use subtraction to do this comparison. We say that person has $4 more. And so when you're doing a comparison, you're really trying to answer this following question. Find what needs to be added to B to produce A. So when you see A minus B, it's the operation here is the resolution to a missing addend task. So it's like saying, hey, you start with A, add what amount, and you're going to get B. Well, this is solved by doing, what needs to be added to B to get A. So I got my A and B in the wrong places. What needs to be added to B to produce A? So to solve this, you would subtract B from A. You can think of this as subtraction as being the missing addend task. And this establishes that comparison between the two. So we're going to frame our comparison this way. When we see subtraction, a minus b, think of this as, okay, what do I need to add to b to make a? So when I see 6 minus 2, I'm saying, okay, what do I need to add to 2? 2 plus what will give me 6? And we're going to use integer chips to model this. So we're going to do a representation of 2, which is a plus plus, a representation of 6, which is a plus 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 plus, and then just put them side by side and say, okay, the question mark is going to be answered by what needs to be put right here, right, so that I've changed 2 into 6. Of course, one way you could do this would be to line up what you already have, like cancel those pairs, and then see, hey, what's left out of the 6? 4 pluses, right? This is what we need to add to 2 to get 6. So if you're doing integers, chips over here, it'd be a good idea if you're doing a comparison is to put the two values, don't think remove, right? Put the 2 on here. Then let's do a 6 on here as well. And we're trying to say, hey, what do I need to add to that first row so that we have the same, so it matches the second row. And so here you get to say, okay, well, those already align, those already match, those already match. So you can clearly see we just need to put those 4 pluses. And so the result, or the question mark that we're trying to answer here, is 4 pluses. So this tells us that 6 minus 2 is 4. In other words, that you need to add 4 to 2 to get 6. Or you can say that 6 is 4 more than 2, right? Hence the comparison. Nothing was really being taken away, right? We didn't start with 6 and then I say remove 2, what's left? So there wasn't that sort of dynamic action happening here, that mental operation. Instead, it was putting 2 side by side with 6 and saying, how do they compare? What needs to be added to the 2 so that's the same thing as the 6? Okay, let's do the 2 minus 5, same approach. When you see 2 minus 5, you're really trying to say, okay, well, 5 needs to be added to what to make 2? All right, let's put them side by side. 5 needs to be added to what to make 2? Okay, so we have the representation for 5, plus, 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 and a representation for 2 is just plus, plus. And you say, okay, what needs to be added to 5 to make 2? Well, I need to combine 3 negatives with 5. If I do that, then we'll have those 0 pairs, right? And they'll cancel, and you'll get 2. Okay, so what needs to be added to 5 to make 2? Well, you need to cancel some of the 5, so you need to add some negatives. Right. Canceling those, we have 3 0 pairs there, and we're left with 2. If you want, you could put the box like over here saying, okay, I'm going to combine 5 with what so that the result is 2. And that what should be 3 minuses. Up here it was 3 plus, or sorry, 4 pluses. So combine 5 pluses with 3 negatives. Those cancel out and you get the 2. Okay, so using comparison model, we get the answer is we need 4 minuses, so that corresponds to a negative, sorry, not 4, we need 3 minuses, so that corresponds to a negative 3 is the answer. What needs to be added to 5 to make 2? You need to add negative 3 to 5 to get 2. Negative 7 minus negative 2. Okay, so we're saying what needs to be added to negative 2 plus what will make it negative 7. All right, well, negative 2 starts off with 2 negatives, and negative 7 is 7 negatives. And we're saying, hey, what needs to be added to this first one? What needs to go right here so that I would change negative 2 to negative 7? Well, that just means 5 more negatives. Right. Add 5 more negatives to that, and we get an answer. The answer to this question is 5 negatives, negative 5. You can see that when you compare it to the removing or the takeaway model, there is a subtle distinctions here. right? I didn't start with -7 and ask myself what do I, and then tell myself to remove 2 negatives and see what you wind up with. Instead, I asked myself what needs to be added to -2 to make -7, right? So it's a different thought process, but it's also an equally valid way to think about subtraction. Let's do -1 minus -4, right? So we're asking ourselves, hey, -4 plus what amount will make -1? Well, -4, what does it look like? It's 4 negatives. -1 is just 1 negative. And I'm trying to say, hey, what needs to be added to -4 to make it -1? Right? So we're going to combine -4 with something. And in order to cancel 3 of those negatives, I need to put 3 positives. Right? These 3 positives here will cancel 3 of those negatives, leaving just -1. So to turn -4 into -1 by addition, combine -4 with +3, and you will get -1. So the answer to our question is 4 positives. Or sorry, 3 positives, which is, +3. Let's compare -3 and 6. -3 and 6. So we're saying, okay, what needs to be added to 6? So 6 plus what will take you to -3. Okay, well, representation for 6 is 6 positives. A representation for -3 is 3 negatives. Well, in order to, we don't want to add positives to positives. That just makes more positives. We've got to start adding a bunch of negatives to this. Right, so our question mark is, hey, what needs to be added to the end here so that I could turn 6 into -3? Well, you got to do at least 6 negatives to cancel the 6 positives. But then you need 3 more negatives so that the end result is -3. Right? I think you can see, right? 9 negatives are in this here. So our question mark, we needed 1, 2, 3, 4, 5, 6, 7, 8, 9 negatives in order to turn 6 into -3. Right, you could also do a number line here. I didn't ask you to do this here in the notes, but when you're asking yourself, hey, 6 plus what equals -3, you got your number line. I'm going to get rid of that. You start at 6 and you're adding, you want to get to -3, and you're saying, hey, what do I need to add right to 6 to turn it to -3? Well, because you're adding, you want to add a negative. So you would add -9 to 6. That should take it to -3. So you can think of it the visual as well, like how do I go from 6 to -3 by adding, and what number would I need to add to do that? And that's one way to interpret the comparison here. Is we're comparing -3 and 6. And what we're saying is that 6 is, or -3 is 9 units to the left of 6, right? When you get this -9. Let's look back at the comparison up here, what 6 minus 2 means. And think of this in terms of a frame of reference. 6 minus 2 is 4. What we're trying to say is that 6 is 4 units to the right of 2. And so when I do -3 minus 6, we're saying -3 is is 9 units to the left of 6. In other words, -9 is the comparison. It's like kind of saying, hey, if we say 6 is the position 0, then what's the position of -3, right? So if you convert -6, say, hey, that's now position 0, right? Where's -3? Well, -3 would be at -9, right? You see, we're establishing a comparison between, oops, I meant to say +6 there, not negative. We're establishing a comparison between these numbers by saying how far apart they are and what direction, right? If you think about that idea with subtraction up here, right, this easier case to think about, 6 minus 2 is 4. What we're trying to say is that the first number is 4 units to the right, because the result is positive, is 4 units to the right of the subtrahend. In other words, the minuend is 4 units to the right of the subtrahend. That's what 6 minus 2 equals 4 with a comparison flavor means. And when you do the comparison flavor here, we're saying -3 is 9 units to the left of 6. So the comparison here, because I went left, is negative. -9 is our comparison. 9 units to the left of 6. And you can see how this idea of, in fact, well, let's use comparison to answer this. Where's 8 relative to -4? Okay, so if you did a number line, right, -4 is here, 8's over here somewhere. And where is 8 relative to -4? Well, it's 12 units to the right. So we're saying that 8, the position of 8 relative to negative 4 is 12, meaning it's 12 units to the right of negative 4. Right? It's just rescaling this so that negative 4 is 0 and 8 would be at 12. Right? You can see the frame of reference idea happening here when you do a comparison of, and when you interpret subtraction as a comparison, and then you do that comparison with a frame of reference, we are really just finding how far apart these two numbers are and what direction. But if I'm doing integer chips to do this, then I would say, okay, a comparison question would be, okay, what do I need to add to negative 4? So negative 4 plus what will turn it into 8. All right, well, a representation of negative 4 is just 4 negatives, and a representation of 8 is 8 positives. I think one more, there we go. And what do I need to add to 4, right? What needs to be put right here so that when I combine it with negative 4, I wind up getting that positive 8? And the answer to this is you need to have, well, you need to get rid of the 4 negatives. So we need 4 positives to get rid of the 4 negatives, but then you need another 8 positives to get us up to 8 again. So the number of positives I just put in there is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, 12 positives is what needs to be added to a debt of negative 4. Or you can put it this way, 12 credits added to a debt combined with a debt of negative 4 leads to you having a net value of 8 credits. Okay, let's move on. So subtraction is a very rich operation. I mean, some of these ways of thinking are not necessarily intuitive to a child initially, but when they practice with these manipulatives, they do get to the point where these ways of thinking become more second nature. Another approach to integer subtraction is to use a number line. Okay, so you're doing integer subtraction. 2 minus 5. Okay, so we begin at the position indicated by the minuend. So at position 2. And then if subtracting a positive value, you move to the left. If subtracting a negative value, you move to the right. Because subtracting a negative value is like removing a debt. That's like adding an asset. You know, you get more value if you remove debts. And so if I do 2 minus 5, so I'm subtracting a positive. When you subtract a positive, you go left that indicated amount. So we say minus 5, go left, and that's going to take us to a position of minus 3. I'll leave off all the hash marks, but there's 1, 0, negative 1, negative 2, and then negative 3. So this result is negative 3. Negative 3 minus 6, so start at negative 3. There's negative 3, which is, there's 0. You don't have to put 0 in there, but just remember negative 3 is 3 units left of 0. And if I remove positive 6, to remove a positive, you go left. So I want to go left 6. 1, 2, 3, 4, 5, 6. Let's indicate our start and stops a little bit better. And I removed 6. And when you go left 6, that takes you to right negative 9. And negative 4 minus, or sorry, negative 1 minus negative 4. We do a number line. Let's make that look a little more straight. Good enough. And start at position negative 1, which is 1 unit left of 0. And when you remove a negative, when you remove debts, you add assets. So you go to the right 4 units in this case. So 1 unit takes us to 0, then 2, 3, 4. When you remove a negative 4, you go to the right, takes us to this location, and that's at position 3. So here's some ways that, you know, using these number lines that people like to do to model subtraction of integers. Subtract a positive, go left, subtract a negative, go right. Right? It's easy to confuse it with the rules for the adding, right? If you add a positive, you go right, but if you add a negative, you go left. But if you subtract a positive, you go left. You subtract a negative, you go right. Did I say that right? Subtract a positive, you go left. Subtract a negative, you go right. Not to be confused with the rules for adding. Adding a negative, you go left. Adding a positive, you go right. And I prefer the comparison ideas or the takeaway models using chips over just doing this sort of memorized rules about knowing when to go left or right, because that is not as sensible to a student, and hence it makes math feel inaccessible or just sort of magical to them. Just a bunch of rules they have to learn and memorize but not understand. All right, use integer chips to calculate the results of the following operations. Generalize your calculations to show that subtracting a positive integer is equivalent to adding the opposite integer. So let's do 4 minus 6, and we're going to do the, let's do the takeaway model. It doesn't say which model, takeaway or comparison. Well, let's do takeaway. We have 4, and I want to remove 6. So 4 is 4 plus signs, and I want to remove 6 plus signs. Well, I don't have 6 plus signs, so I've got to put some plus minus pairs in there, some 0 pairs. So now I do see 6 plus signs, and so now I can remove it. Remove the 6 plus signs. And then the result of doing that is we have just 2 minus signs. So we get negative 2. Let me put the result down here, equals negative 2. All right, well, if I do 4 plus negative 6, let's see what the result is. Four, and I'm going to do let's do the horizontal. 4 is plus 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 plus, and we're going to combine that with negative 6. And we wind up getting 0 pairings. Oh, negative 6, there we go. We get some 0 pairings here, and so the result is, right, these get combined because we're doing addition here, right? Subtraction is a takeaway model, and addition is a combining model. And the result is 2 negatives. Okay, so to remove 6 credits, is that the same thing? Let's think of this as money. So we have 4 credits, and I remove 6 credits. But just the idea of removing, forget that we had 4 to begin with, that doesn't even matter. If you remove 6 credits, that's like adding 6 debts. Right? What if I had 5 minus 2, remove 2 from 5, right, so you have 5 plus signs, and you remove, well, that's 6 plus signs, and you remove 2 of them, you have 3 plus signs left. But if you do 5 plus negative 2 instead, right, combine 5 plus signs with 2 negative signs, that's going to have the same effect as just removing the 2 plus signs to begin with, right? Adding negative 2 to positive 5 has the same effect as just removing positive 2 from positive 5. And, you work through several other examples if you like, but you want to generalize the result, get to the idea where you feel like you can justify the following claim, which is, this claim right here, that subtracting a positive integer is equivalent to adding the opposite. So subtracting 6 is equivalent to adding negative 6. Use integer chips to calculate the results below. So we have 2 minus negative 3. So we're going to do the takeaway model. We have 2. Or maybe I could do the comparison model. Well, I want to say, hey, negative 3 plus what will give me 2. Or if you're doing comparison, you're saying, hey, what if negative 3 is position 0, then where's 2 at, right? If you rescale this so that negative 3 is position 0, then you would say, well, then 2 would be at position 5. So I expect an answer of 5 out of this using the number line comparison idea. It's the subtrahend you set your frame of reference, 0 it out right there. So negative 3 is at position 0, and then you're asking yourself, hey, where's number 2 relative to negative 3? Well, if negative 3 is at position 0, then 2 would be at position 5. In other words, it's 5 units to the right of negative 3. Okay, but we're doing integer chips here, not a number line. to do a comparison. So we have negative 3 is represented by 3 negatives, 2 is represented by 2 positives, and we're saying, okay, what do I need to add, right? What needs to be combined to negative 3 so that the end result will be 3 positives? Sorry, 2 positives. Well, I need 3 positives to cancel the 3 negatives, and then I need 2 extra positives, and you can see that we get a result of 5. And so we have 2, or the result here is a positive 5. 1, 2, 3, 4, 5. 5 is what needs to be added to negative 3 to make 2. Or if you do the takeaway model, right, here's a representation of 2. It's plus plus. And I want to remove 3 negatives. Well, I don't have 3 negatives, so put some 0 pairings in there. So now I do have 3 negatives I can remove. And right, and the results will be the 5 pluses. And there's the takeaway model of subtraction using integer chips. And now let's do 2 plus 3. Obviously 2 plus 3, we have plus plus, and we're going to combine it with plus plus plus, right? Combine those. And the result is plus 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 plus, 5 pluses. I kind of like using this takeaway model, because to remove negatives from positives, I had to insert more positives so that I could remove the negatives. Right, so if I started with 2 and I had to remove 3 negatives, I had to essentially add 3 more 0 pairs so I can remove those negatives. And then the result was I had the 5 positives. Well, removing 3 negatives from 0 is like just adding 3 positives. So we start with 2 and we add 3. So you do enough thinking this way, and you start to build up the rule that, okay, removing negatives is the same thing as just adding positives. Whereas up above, we saw that removing positives is the same thing as adding negatives. So in other words, you could overgeneralize and say that subtracting an integer is like adding its opposite. Right? So if you subtract a negative, then you want to add the positive. But if you subtract a positive, you want to add the negative. So that's a higher level generalization. Subtracting an integer is like adding its opposite. Perform the following calculations. Recall that subtraction is not commutative, but if we convert subtraction to addition with the opposite, then we can use the commutative property of addition. Right? We're not going to bother with the chips here, but 7 minus 5 is 2, and 5 minus 7 is negative 2. So we can see here that subtraction is not commutative. However, if I say that 7 change subtraction to addition but with the opposite, this I can flip around. I can, because addition is commutative. So if you do want to flip, the 7 and 5 around, you have to do it in the following way, right? 7 minus 5 is not the same thing as 5 minus 7, so don't flip them around like that. But you can rewrite 7 minus 5 as negative 5 plus 7. Right? All of these answers, they all give you 2. You can do the same thing here. You can write this as 5 plus negative 7. That also will give you negative 2. Right here I'm doing a takeaway model. Here I'm doing a combined model, but both models will give you a negative 2 result. And because of the addition now, you could write this as negative 7 plus 5, and that's going to give you a negative 2 as well. Notice my use of parentheses. I really like using the parentheses when you're doing an operation followed by a negative number. When you're doing an operation followed by a positive number, then I usually don't bother with the parentheses. And then some people don't bother with them at all. They'll just say 5 plus negative 7 and write that down. But I personally don't like seeing the operation followed by a sign right away like that. I like to put the negative number in parentheses. It just looks a little bit better. In the case over here, you have to be careful about how you do this. When you're doing an operation that has pluses and minuses, but no parentheses to establish order, then you should go in the order that you see them. So in other words, you should do the 6 minus 3 first and get 3, and then add the 2. So the real result here should be 5. Some people their brain will accidentally do this set of parentheses. And if you add 3 and 2 first and get 5, and then remove 5 from 6, you get a different answer. Right, so be careful you don't do that. When there are no parentheses, just go left or right. Right, left to right of operations. Do that first, and then do the plus 2 next. We've already seen that I can't switch these around, right? I can't switch 6 minus 3 to 3 minus 6, because that would be negative 3 plus 2, negative 1. You get even a different answer. But what you can do is this. You can say 6, all the subtractions turn to additions, but with a negative number. And now I just have nothing but additions. Now I'm free to do all sorts of commutative. I could do negative 3 plus 2 first. This is the associative property. Do that one first. You get negative 1. Add to 6. You get 5. Right? Associative property. You could do that first. 6 plus negative 3 is 3, and then add 2. You get 5. You could do commutative properties. Do the 6 plus 2, and then add the negative 3. So you can get 8, and then add negative 3 to that. And put that in parentheses. That also gives you 5. If you can switch it around and then go back to subtraction. So you could say do this instead. 6 plus 2 is 8, and then subtract 3, and you get 5. Right. You could put the negative 3 first. Negative 3 plus 2, and then plus 6. Right. Add those first. You get negative 1, then add 6, you get 5. Right. Or add these first. 8, and then add the negative 3 to that. You get 5. So once you turn all the subtractions to addition with a negative, and it's nothing but addition and addition, then you have a lot more freedom with how you go about doing this. You can use associative properties, commutative properties, whatever you want. That's true for addition. Just turn all your subtractions into additions with a negative, and you have a lot of freedom. All right, integer multiplication. Integer multiplication can be performed by interpreting a positive multiplier as combining the indicated number of copies of the multiplicand, and a negative multiplier as removing the indicated number of copies of the multiplicand. Okay, so when you see a positive 4 times a 3, and notice I'm only putting the number now after the operation in parentheses. I'm not bothering anymore putting the leading number of the operation in parentheses, just the one that follows. That's especially useful in a case like this. Like if you have 4 times negative 3, and let's say you're using a dot instead, and sometimes people don't see the dot and they just see this and they think you're doing subtraction, right? All sorts of things can go wrong. But if you put the second number in parentheses, even if you do it a dot that someone can't see, oops, like in doing a minus, then people are just going to see this, but that's still the same meaning as to do multiplication. We're going to wind up getting a negative number here, by the way, but let's build up to that using integer chips. 4 times 3 means we want to do 4 copies of 3. Let's move those down. Okay, so there's 4 copies of 3, and that gives us 12. So we want to combine. Let's see, when we have a positive multiplier, I'm reading this part here, a positive multiplier is combining the indicated number of copies of the multiplicand. So the multiplicand here is the 3. And we have, so there's the 3 using chips. Here's a second copy of 3, a third copy of 3, and a fourth copy of 3. All right, so we're going to combine 4 copies of 3. And then the result here is, of course, 12. 12 plus signs. So positive 12 is the result. Here, we're going to combine 4 copies of negative 3. All right, so on our this would be, all these want to be negatives. So there's 4 copies of negative 3. Right, and we combine them and we get, there's negative 3, here's negative 3, here's negative 3, here's negative 3. Do 4 copies and the result is negative 12. Now when the multiplier is negative, notice we had a positive multipliers for both of these, 4 and 4. But now I'm going to switch to negative 4 as the multiplier, and negative 4 as the multiplier. Also, you'll notice that I'm varying my symbols for multiplication, using the times sign, using just parentheses with a number in front, using a dot, and using that asterisk. All of those mean to do multiplication. And negative 4 dot 3, so negative 4 times 3. So when it's a negative multiplier, let's read this, a negative multiplier as removing the indicated number of copies of the multiplicand. Okay, so we can do, imagine doing 4 copies of 3. but then remove those from a 0. So you want to create these 0 pairs, so you have all these negatives. And if you remove 4 copies of 3 from something, that's like removing 12 from something. Right? If you remove 4 copies of 3, then you're removing 12. That leaves negative 12, essentially. As far as the frame of reference goes, when you remove 12 from something, it's like adding negative 12 to it. And maybe this is a good way to think about doing it. Right? So you do 4 copies of 3, but then when you remove them, you're left with negative 12. Imagine removing 4 copies of negative 3 from 0. Sorry, 4 copies of 3 from 0. So if I started with 0, or then, right, here's me like starting with 0. Imagine you have 12 0 pairs. So here's 0, and I want to remove 4 copies of 3. 4 copies of negative 3. Sorry, 4 copies of 3. And so there's 1 copy of 3. Here's a second copy of 3. A third copy of 3. And a fourth copy of 3. Remove them, and you're left with negative 12. So 4 copies of 3. And I'm going to put the 0 pairs over here. So we're starting with 0. And now we're going to remove 4 copies of 3. And the result is negative 12. Some people like to say, hey, when you do negative 4 times 3, just do 4 copies of 3, but then do the opposite sign of that, and then change the sign. So you just do 4 times 3, and then do the opposite sign, negative 12. So there's a variety of ways you might want to think about a negative multiplier. This one here, when I see negative 4 times negative 3, I'm thinking I'm going to remove 4 copies of negative 3 from 0. So I'm going to copy this again. But this time, we want to so there's my 0 right there. But I'm going to remove 4 copies of negative 3. So I'm going to remove those actually this time. And the result is positive 12. So positive multipliers mean to combine. And then negative multipliers are to remove so many copies of the multiplicand. Use integer chips to show that the above operations are numerically commutative. Okay, so let's do these all backwards. Let's do 3 times 4. Well, this means combine 3 copies of 4. And I'll just do, vertical. There's a copy of 4, second copy of 4, third copy of 4. Because I'm just doing them vertical, you can see that in the end I have 12. I have the exact same shape I made right there. I'm just making my groups be vertical. So there's a copy of 4, copy of 4, copy of 4. Or you can do 4 copies of 3. Right? This grid approach is really nice for showing that multiplication is numerically commutative. And the result is 12. Let's do the other one reverse order. So I'm going to do negative 3 times 4. Let's see what that means. Negative 3 times 4. This means remove 3 copies of 4. So I need to have essentially it's going to look like this again. Remove 3 copies of 4. Right, the copies are just vertical now, right? There's a copy, there's a copy, there's a copy. Remove 3 copies of 4 from 0, and the result is you have negative 12. Let's do this one here, reverse order. 3 copies of negative 4. Okay, well, here's 1 copy of negative 4. Here's a second copy of negative 4, and a third copy of negative 4. I'm doing columns this time as my copies, just so that I can make the exact same grid you're essentially seeing there. But 3 copies of negative 4 make negative 12 when combined. And then finally, the last one, let's remove 3 copies of negative 4. Remove 3 copies of negative 4. It's going to really wind up being this result. Just that your copies now are, there's 1 copy of negative 4, a second, and a third. Remove 3 copies of negative 4, and we get 12 left. Now you might start seeing some rules emerge that you're already familiar with. If you multiply 2 positives, you get a positive. If you multiply a positive and negative, you're going to wind up with a negative. And if you multiply 2 negatives, you're going to wind up with a positive, right, using these models. And also, we are seeing that integer multiplication is also commutative, just like whole number multiplication was. Consider the operations below where the multiplier is negative 1. Okay, so this is like remove 1 copy of 3. So let me make, here's 1 copy of 3, but we have a 0, so we start with 0, and remove 1 copy of 3, so remove that, and we are left with negative 3 as the result. And over here, it's similar, except we're removing 1 copy of negative 3. So what's being removed is changing. Move that over there. Remove 1 copy of negative 3, and the result is positive 3. This is just to illustrate that even with these meanings, when you multiply a number by negative 1, you really just wind up changing, it converts it to its opposite. Right, when you multiply negative 1 times 3, then it converts 3 to its opposite, which is negative 3. If you multiply negative 1 times negative 3, it converts negative 3 to its opposite, 3. Multiplication by negative 1 simply turns a number into its opposite, turns an integer into its opposite. Okay, this is our last slide for today. It's integer division. We have partitive and quotative meanings for division that we talked about in the last unit. And we're going to use those meanings to help do some division. As a reminder, partitive division is the missing multiplicand model for division. So we know the number of copies, we don't know how much there is per copy, and we know the resulting amount. And the goal is to find the missing multiplicand. So you interpret A divided by B is the answer to B copies of what amount. So the what amount is the multiplicand. Right, you're essentially saying B copies times what amount give you the amount A. B copies of what make it A. Remember, I'm always assuming the first number in multiplication is the multiplier and the second number is the multiplicand. All right, so when I see 8 divided by 4, I'm saying, okay, 4 copies of what make 8. Or we can say 4 times what makes 8. Now in this case here, it's going to be 4 copies of 2, right? You could do the model where here's your 4 copies, and you have 8 things, and you're essentially doing fair sharing. That's 9, that's not 8. There we go. And you're saying, okay, I'm going to start passing these things out, like just sharing them. Oops. What just happened? It went away. You're right, you get the idea. Sharing these things. Did not mean to do that. Cancel that. And we wind up with this. We get an answer. Okay, I can see that there's 2 per copy. 4 copies of 2 will make 8. Partitive division, sometimes called the sharing division for that reason. It's like sharing 8 candies with 4 kids. And the answer here is, if you want to think in terms of integer chips, you would say, okay, combine 4 copies of what to make 8? Well, think of it backwards, right? Here's the 8 integer chips. There's the representation of 8. And you're just breaking this into groups of 4. And you're saying, okay, we have 4 copies of how much is in each copy. So we want to combine 4 copies of positive 2, right, to get positive 8. And so maybe that's what I want to leave here. So we want to do this with integer chips. So we would say 8 is represented by having, 8 plus signs, and you're putting them into groups of 4, which sometimes it's easy, you can see what those groups are. And we would say, okay, the amount per copy is we have 2 per copy. Positive 2 per copy. So the answer to this question is 2. In other words, this is a justification for that 8 divided by 4 is equal to 2. Okay, so let's continue. Let's do everything with partitive first, and then we'll do the second meaning for division. And let's involve some negatives. Okay, this next one is saying, okay, negative 2 copies of what make 10? So negative 2 times what will make 10? Well, remember that negative 2 means you're removing. If you start with 0, let's pretend like we have a 0 here, and we want to remove 2 copies of something. If we remove positives, we're going to be left with negatives. In order to produce a positive 10, I can't remove positives, I have to remove negatives. Right, so it's the negatives here that need to be removed. Right? Take negatives away from 0, you get positives. If you take positives away from 0, you get negatives. And keep in mind that when you have a negative multiplier, right, we are trying to remove copies. We want to remove 2 copies of something to make 10. All right, so I'm going to just think of this backwards. I'm going to create 10 zeros, so I can see 10 pluses and 10 minuses. Let me do it this way. Delete. 10 pluses. 10, and I think I did too many. Yeah, I did too many. I did 11. There we go. There's 10 pluses, 10 minuses. Okay, I want to remove 2 copies of something so that the result is 10. So I really want to remove all of these negatives. Right? I want those to go away so that I have 10. So just break that into groups of 2, and you can see that if I remove a negative 5 and a second negative 5. So what I'm thinking here is I need to remove 2 copies of negative 5 to make positive 10. Right? So that's what this structure, and this is what we're trying to find here. Remove 2 copies of what to make positive 10? We'll remove those 2 copies of negative 5. So the answer to this question is negative 5, which justifies the fact that 10 divided by negative 2, using a partitive meaning, should give you negative 5. Remove 2 copies of negative 5 to get positive 10. Next one. Here we're saying, okay, 5 copies of what make negative 15? So now we're doing, when we have a positive multiplier, we're combining copies. So we can just start with a representation of negative 15. There's no removing happening, so we can just say, okay, negative 15 is, I'll do it in groups of 5, I'll make it easier. There's negative 15. And you can see that if we break this into 5 groups, essentially, zoom in here. And we can see that there's negative 3 per group, per copy. Right, each column is a copy. Negative 3 per copy. So if I combine 5 copies of negative 3, then I'll have negative 15. So we answered this missing multiplicand task. 5 copies of negative 3 will make negative 15. So this supports the fact that negative 15 divided by 5, using a partitive meaning, is negative 3. Right? 5 copies of negative 3 will make negative 15. Right? Whereas up here, because we would remove 2 copies of negative 5, that leads to positive 10. And up here it was 4 copies of 2 make 8. And let's do this last one here, negative 12 divided by negative 4. So we're saying negative 4 times what will give me negative 12. So if I want to remove 4 copies and produce negative 12, I need to remove positives. So I'm going to start with 0. Remember, we're doing a removal, so I have to start with 0. I'm not combining copies of things. I need 3 more. There we go. So there's 12. Let me just make sure I can see them. Okay, there's 12 pluses, but let's put 0 in here. So I got to put 12 minuses as well. So I have 12 0 pairs. And when you see this -4 times, we're saying remove 4 copies of what to make -12. So I need to remove these 4. I need to get rid of those pluses to make -12. So you break those into, let me move this down a little bit. Oops, there you go. And I want to remove the pluses so that the result will be a minus. So you have 12 pluses, and we want to do that in 4 copies, and so the copies will be groups of 3 pluses. Right? So if what I just circled, we're going to remove 4 copies, right? That's what a -4 multiplier means to do. Remove 4 copies of +3 to get our -12. Okay, so it was how much was there per copy was the answer of our division task. So -12 divided by -4 is +3. Remove 4 copies of 3 will yield a -12. Okay, and this is our partitive meaning for division. Let's do quotative. Quotative is when you're doing a missing multiplier task. So A divided by B is a way to answer how many copies of B, so you know the multiplicand, that's B, but you don't know the multiplier, are combined or removed to make the amount A. So we have, we don't know how many copies there are, but we're copying B so many times to make A. We're trying to figure out how many copies of B make A. And we have to think about, are they combined or removed to make A? Because now we're working with integers, with negatives. So 8 divided by 4 translates into how many copies of 4 are either combined or removed. We'll have to decide which we're doing here to make 8. Well, if I'm starting with, so I'm copying 4, and I'm trying to count how many copies. So if I have, there's a representation of 4. A second copy will make 8. But if you're starting with a positive and you're trying to result in a positive, then you don't need to do removing, you need to do combining. Right? So the first thing we want to settle on is that we are going to combine, not remove in this case. We want to combine copies of 4 to make 8. Right? When they're both positive, then you just need to do combining to make it happen. And so then I'll repeat the model I just had. Right? You can start with the 8, start with the end amount, and then start grouping them in groups of 4, right? And I see 2 copies of 4 will equal 8. We'll combine to make 8. So the answer to this question was, we're trying to find how many copies. So 8 divided by 4, the answer is 2. Because 2 copies of 4 make 8. Now notice how that's different from our partitive thinking, right? Here we assumed 4 was the number of copies, and we're trying to figure out how much was there per copy. Where in this one here, we're saying 4 is the number of amount per copy, and we're trying to find how many copies. And so when I summarize my findings here, we all know that 2 copies of 4 make 8. But the meanings of the 2 and 4, also 4 copies of 2 make 8. The meanings of the 4 and 2 are different in each case. Here we were saying 4 copies of 2 make 8. Here we're saying 2 copies of 4 make 8. Okay, let's do this next one. We're doing 10 divided by -2. So this is how many copies of negative 2. How many copies of negative 2 are combined or removed to make negative or positive 10. All right, so when you see that, now you're working with copies of negative 2. Here's negative 2, and we're trying to get to positive 10, right? It's a bunch of positives. Well, I can't combine, if I combine a bunch of negatives, I just get more and more negative. I can't combine negatives to make a positive. And so this tells me that we will not be doing any combining. Instead, we'll be doing removing. We've got to remove copies of negative 2 to make negative 10. So I know that the result we want to be 10. So let me write down a representation for the 10. 1, 2, 3, 4, 5, 1, 2, 3. Okay, so there's my 10. And here's all the negatives. So that we have 0 on the board right now. And we need to how many copies of negative 2 are removed? So we need to remove negative 2s, a bunch of negative 2s, and to make 10. So 1, 2, 3, 4, 5. So if we remove 5 copies of negative 2, we will get 10. Which means our multiplier should be negative because we're removing, and negative 5 is the multiplier. Let me write it this way. The multiplier is negative 5 because we're removing 5 copies of negative 2 to get 10. And therefore, this leads to the justification that 10 divided by negative 2 is equal to negative 5. Right, because we remove 5 copies of negative 2, and that will make 10. Whereas over here, I said we removed, it's backwards, the multiplier is here now. We removed 2 copies of negative 5, that makes 10. But over here it was, we remove 5 copies of negative 2, that makes 10. Okay, quotative meaning for negative 15 divided by 5. So we're going to say how many copies of 5? How many copies of 5 are combined or removed? We'll have to make a decision about which one we're doing to make negative 15. Okay, so we have negative 15. There we go. We have copies of 5. So here's a 5. I can't just make copies of 5 because that's going to make positives that are larger. We're trying to make negative 15. So I'm going to have to do removing 5s to get to the negative. And so this tells us that we do not want to combine positives to make a negative. We want to remove positives to make a negative. Okay, so let's start with a representation of the negative. Well, let's do 15 negatives. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 15 positives. 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And how many copies of 5 need to be removed to make negative 15? Right, well, there's 1 copy of 5. There's a second copy of 5, and there's a third copy of 5. So I'm saying that if we remove 3 copies of 5 to get negative 15. But the removing 3 means that the multiplier is negative 3. Multiplier is negative 3. So this tells us that when we're doing a quotative meaning that negative 15 divided by 5 gives me negative 3. Because we remove 3 copies of 5 to get negative 15. Oh, and then finally the last one, negative 12 divided by 4. So this one is negative 4, or how many copies of negative 4? How many copies of negative 4 are combined or removed, we'll have to make a decision about which it is, to make negative 12. Well, if you combine, here's negative 4 is negative, negative. You can just copy negative 4, and eventually you'll get to negative 12 in this case. So we don't need to do any removal because the signs, they're both negative. And so in this case, no removal, just a simple combining of negatives to make more negatives. Let's begin with the negative 12 representation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there's 12 there. And I don't need to start with zeros. When I'm doing the removing is when I start with 0, and I'm saying what needs to be removed to yield the result. But when you're combining, you just, here's negative 12, and figure out what it was that we combined to get to it. Well, there's one group of there's one copy of negative 4, a second copy, and a third copy of negative 4. Right? So we're going to combine 3 copies of negative 4, and that will get to negative 12. So the fact that we're combining 3 copies means the multiplier is positive 3. So this leads to negative 12 divided by negative 4 is positive 3. Because 3 copies of negative 4 will make negative 12. All right, so there are the partitive and quotative interpretations of division when you are working with positive and negative numbers. When you're working with integers, there's a lot to digest here. Subtle differences in the ways of thinking that I'm trying to make explicit in your own thinking so you can categorize them for yourself and really try to analyze whether you are thinking partitively or quotatively when you answer a division question.